the idea was that a term would just be a string of symbols syntactically. So there'd be a variable and we'd say such that sign and then this formula phi of our language. So this is kind of an unofficial gadget that we're going to use as a sort of abbreviation. And this definition here says precisely what are terms. Variables that count as terms, but these gadgets, these are with the brackets around, are called class terms. And we don't have to use these. They're entirely eliminable. And the process of eliminating them is given by these clauses down here. So if I were to come across a term in a formula that I've written out, I can always get rid of it by using this kind of explanatory recursion that's down here. So I'll talk about generalized formulae, and these will be ones which have terms in. So further to recap, we saw there was a way we can just think of V as being, well, a term, the class of x's that equal themselves. And various other definitions of straightforward objects that we have here. Ordered pairs I can think of as being the term that's given by, well, I've just explicitly written them out, singleton x and doubleton xy. So let's consider the axioms then. So besides the axiom of extensionality, we had this empty set axiom, and this just says very neatly what it is. It just says this thing that I named in the definition above to be the empty set is a member of V. So that's just a way of saying it's a set. Because V will be the collection of all of our sets. V was the collection of everything that equals itself. The pairing set axiom just says, implicitly here, there's for any x and y, a quantifier, this thing here is always going to be a set in V. And the big union of these objects here is this object x. This will always be a set in V. So in fact, to say that something is in V is just tantamount to saying there is a set that it equals. So I can write down, say, something that says a term is in V, and that just means there is a set which it equals. So the idea is that really we can only legitimately write something down to the left of the epsilon sign if it's a set. This is our motivation here. We don't want to have proper classes like the Russell class or V itself to be on the left of the epsilon symbol. So are there any queries at this point? Anything I should clear up? Okay. Well, unless you interrupt me, I will continue. I'll try and talk not everything just from the notes. It's a bit boring just to have somebody read out the notes to you, but here I'm just sort of recapping a little bit. I'll do some writing on paper later, and I hope my other camera will be good for that. So the axioms that we've got so far, just talking about pairing, and if I've got union, well, I can always then take perhaps three things and put them together. I can always talk about taking sets x and y and putting those together. So, for example, to prove that x union y is a set in V, well, axiom 2 says, okay, as a start, the unordered pair xy is a set in V. And then axiom 3 will say I can apply union to this thing that I've justified as a set, and this will be a set. But lo and behold, it's like an exercise from, or an observation from the elementary set theory class. This big union is just another way of writing x union y. Right. So this is the same as this. And if you're pedantic, it's by the axiom of extensionality. These two guys have got the same elements. Okay, so this justifies X union Y's in V. And now if I want to say that for any three things, X1, X2, X3, the unordered triple is in V, excuse me, all I have to do is take the unordered pair X1, X2 and union that up with just the singleton set X3. And that will justify X1, X2, X3 being in V, and so on for any finite n. Now, the next comes quite a slab of notations, really, some of which will be familiar and some you may have perhaps forgotten from the set theory course. I think of a relation as just being a binary relation. So just a relation between sets. So I can think of it as a subset of just V cross V. It's just a set of ordered pairs. Sorry, it's a class of ordered pairs. R could be a class term here. So, and this is what this Cartesian product is. It's the class of ordered pairs where first thing is a set and the second thing is a set. An n-ary relation is something that's contained in V cross V n times. But notice V cross V n times actually is, if you then look back to what Cartesian product is up here, you'll see actually, if I think of T as V here, so, well, it's n plus 1. V to the n plus 1 is actually just a binary relation. It's a relation between V to the n and V. So actually, a relation which consists of n plus 1 tuples is also officially a binary relation. It's just that the first thing, the first coordinate, is itself an n-tuple. And this ties in with what we've got here. An ordered n-tuple actually is an ordered pair, but the first thing is already an ordered n minus 1 tuple. So this way we don't have to have separate definitions really for ordered triples, ordered quadruples, and so on. We just build them up using ordered pair. This just keeps things simple. So I'm just pausing for a moment. Okay. Okay, back again. So definition 1.6 is now just saying perhaps some more well-known things in part 1. The domain of the relation is the set of first coordinates of the ordered pairs in R. The range of the relation is the collection of second coordinates, the things where something pairs up with it. The field is everything that's in the domain of the range. If I want to restrict a relation to a set U, I use this kind of hook. And that's just the set of pairs that are in the relation, but X must come from U. Now the range of a relation on a set, to be distinguished from the line above, that's the collection of Y's which correspond to an X under the relation where the X is in U. So actually, if R was a function as opposed to a relation, it would be more commonly what we call the range of the function on U. But it works for relations as well, which are not single valued like functions. The inverse of a relation is what it sounds like. I just switch all the ordered pairs around. So where all the xy's become yx's. And this is the composition of two relations. it's the set of ordered pairs xz, where there is some intermediate y, such that x is related to y and y is related to z. I'll let you read definition 1.7 yourself. And now 1.8 here is specializing relations to functions. A function, abbreviated as this, so this is a relation. It says this f gadget here is a function, and it says it's single valued. Right? For any x and y and z, if xy is in the relation f and xz is in the relation f, excuse me, then y equals z. It's single valued. An n-ary function is just one that's a function, and its domain is in contained in n-tuples. And instead of writing something like f of the n-tuple equals y, we just keep it simpler and just write fx1 up to xn equals y. And here in 3 to 6, again, I won't go through them. These just say, give definitions of completely ordinary properties that functions may have, right? Being one-to-one or onto or bijection. And we'll need this definition for the axiom of choice. Again, this may look like something familiar from the very end of the set theory course. This is the collection of functions. This is b to the a in definition 1.91. This is the collection of functions from a into b. Now we're going to define a generalized Cartesian product. So if I think of as a function, it's giving me a list of sets. So, and I'm interested in the Cartesian product of the sets that are in the range of F. So maybe I'll try writing something at this point. So again, keep referring to the notes there. So I think of F as giving me a whole bunch of sets. So speak up if this is going wrong. And we say that the empty set is not in the range of F. So that means that none of these sets inside here, inside this bag, are empty. So none of these equal the empty set. So this is some fx, and this is some fx prime, and this is some fx double prime, and so on. So the idea of a generalized Cartesian product here of these is, well, to be transparent, it's a choice, the collection of choice functions. So it's going to be the collection of functions that pick out one element from each of these sets. And if you then look at the definition, you can see this is exactly what it says once you've puzzled it out. So the Cartesian product here is the collection of h's such that h is a function and its domain is the same as the domain of f. And I pick anything in the domain then this means h of x is a member of f of x. So here is an h picking out things from each element of the things in f of x. So in short, h is a choice function. For the range of f. So it's just a rather mathematical way of saying that in this definition. Okay, I hope that's all right. Go back to the screen share again. Okay, so here are the axioms fully listed out. We've already discussed A0 up to A3. Since we just talked about Cartesian products, jump down to A9, the axiom of choice. Let's see what the axiom then says. Well, we wanted to say, in fact, that every collection of non-empty sets has a choice function, and that's really just what this says. Suppose I've got f as a function, and its domain is a set, and the sets in the range of f are all non-empty, then there's a choice function. So that's one formulation of the axiom of choice. So implicitly in here is the fact that there's no kind of quantification written down, but this is supposed to be, an axiom for each f that I can think of. Here's the power set axiom. We defined the power class of x earlier on. It's the collection of, I don't know where that was actually numbered. So that's definition 1 to 9, line 164. We define the power class. And this says, this is a succinct way of just saying it's a set. Right? So again, there's an implicit for all x here, universal quantifier over sets x. For all x, power set of x is a set. Here is infinity, working up. It says there is a set which contains the empty set, and for any y that's in x, y union singleton y is in x. So the successor of y is in x. So this builds up, starting from the empty set union, the singleton empty set. So that's what we call the number 1. And then 1 union singleton 1 gives me the number 2. 2 union singleton 2 gives me the number 3, and so on. So the infinity axiom just says there is a set that contains all of those gadgets. So it's an infinite set. It doesn't say it's exactly the set of natural numbers, but it's a set that contains them. Let's see the replacement scheme. So for every term f here, if f is a function, then the range of a function on a set is a set. So the idea here is that if you apply a function to a set, you can't get a proper class many things out of it. So again, here, so I think of replacement. I've got here some kind of function, and maybe it takes v to v here, maybe it's defined on all sets. But if I pick out a particular set, x here, and I apply f to the members of x, right, so here are all these things here and sitting inside x, and I apply f to all of these, then the range of f on x, this should be a set as well. So the idea is if I've got a set and I just replace the objects in the set by these things, I've still got a set. I haven't got something that's bigger. So this seems a reasonable property for sets to have. And Frankel actually is in the Zermelo-Frankel axiom system. Frankel gets the credit for this axiom, although actually other people pointed out at the time that somehow Zermelo had missed this one. Okay. Separation scheme, A5. So what is this saying? It says for every term A, right, so unfortunate choice of letter there, A, and for every set X, A intersect X is a set. So here the point is that I think of a term here, what is A? It's going to be the collection of Z's such that phi of Z holds, right, for some formula phi. So this is what terms look like. So what is this saying? It's saying the collection of things that are in A, well, those are the things that satisfy phi, and they're in X. This is a set. So this is going to be the set of Z's in X, such that phi holds of Z. So we've restricted the definition here of A, which could be a proper class here, but we've said we're only going to take the things that are inside X, inside the set X. So basically, this is just a subset of X, of course. So this will be a set. So we can just write it like that. Okay. Last one on the list, foundation. This sometimes looks puzzling at first. Again, we had this at the end of set theory. One reason for using or introducing terms is it gives us a very succinct way of writing out the axioms. So for every term A, if A is not empty, right, so there is something in it right here, then there has to be an epsilon least element. There is an X, which is in A, but there's nothing further down the epsilon tree that belongs to them both. Sorry, this is an and symbol here. This is an intersection. Here's empty. So what we have then is the idea that there is always, for any term, right, I can find some x that's in here, but it's epsilon least in its membership. Excuse me, just a moment. So such an x is an epsilon least element of A. So in particular, what the axiom of foundation rules out are things, are chains, right? Where you can have x as a member of x. So there are no chains like this. And likewise, I can't have chains of different elements like this. So it's saying that the epsilon relation is well founded on sets. Okay. So these are our axioms written out formally. So let's go ahead to, let me skip ahead past this text here and go to 1.3. So in section 1.3 here. So again, definition 111, a set is transitive. Recall it's transitive. It just means any element z of x is actually a subset. So all elements of x are also in x, and so forth. So this gives us a scheme of epsilon induction. Suppose I want to prove that all sets in the universe have some property phi. It would suffice for that to know that a set X inherits property phi from all of its members. So for any set X, if I know that all the members of X have property phi, then X has property phi. Then actually every set has got property phi. And the reason that this would work would be if this antecedent held, but this failed, you would find you would look at the class of x's for which phi failed. And then there would be a epsilon least element of that class of failures by the axiom of foundation. So that least element of that class of failures, all of its members would have property phi, but it itself would not. But that contradicts this antecedent up here. So the axiom of foundation allows us to have this scheme of induction. And if I've got a scheme of induction, I can then define things by transfinite recursion. We were familiar with this in set theory. We define transfinite recursion along epsilon, where epsilon happened to be the less than ordering on ordinals. But it doesn't have to be a linear ordering. All right, did I detect a question or? Okay, thought someone spoke. So we can define functions, a function f, by recursion along epsilon, even if this is, as it is a partial order rather than a linear order, total order. And we do this, we define f of x, assuming I know what f is like on all of the members of x. So given what f is like on members of x, I apply some underlying function g, given to me as a term. I apply g to x and the things I defined so far, and that'll give me f of x. And this is a way of defining a unique function f. And again, it's the axiom of foundation that allows me to do this. So again, so let's go on to 115, definition 115 here, line 305. The transitive closure of sets. Okay, so we defined this again in the set theory course, but I can give it a fancy name. I call it TC, and it's a class term. Right? And I can think of it as given to me by the theorem here. I could define TC of x in terms of TC applied to members of x. So here I am doing it in that style. TC of x. Another function g from that recursion says I take x and then I do some things and I'm allowed to use the function applied to members of x. So I take the union of the function applied to all of the members of x and union that up with x. And this is another way of expressing what is the transitive closure. So the idea of the transitive closure of a set, we wanted the smallest set containing x, which was transitive. So instead of taking an intersection over all of the sets of the universe, a proper class of them that are transitive and contain x, we can build up TCX from below using the recursion scheme here. So another example here is the rank function. So we define the rank function by recursion. Now we thought of the rank function as being the rank of a set X would be the least alpha such that X was a subset of V alpha. But actually you could define the rank function this way. It's just the supremum of 1 plus the ranks of its elements. So again, I'm defining rho X in terms of things I supposedly already know, the rho Ys. And I'm applying an operation G here, which says add 1 to the rho Ys that we know and take their union. And here's the sort of familiar V hierarchy. I just define now the V alpha hierarchy as being the collection of sets of rank less than alpha. So this is different from the set theory course. There we defined the V alphas. We just started off with the empty set, well, as in my intro talk, and we defined V alpha plus 1 as the power set of V alpha. And if lambda is a limit ordinal, then we take the union. Here. So this is an alternative and sort of simpler definition, obviously as a first time through, but we can do this by just saying also V alpha is just the collection of x's whose rank is less than alpha. So there's an alternative way to define the V alphas is you define the rank function first and you collect those together who have got the appropriate rows. And it's an exercise I'd like you to think about is to show that actually these two definitions are the same. So what you do is an induction on alpha the same hierarchy. So, and what you do is it's an induction on alpha show that, let's say V alpha is defined here in 1. As the same as these V primes here, as defined in 2. So that's an exercise in thinking about what the row function is when we've defined it as we did today. Right? So V0 is the same as V0 prime, they're both empty. And then you could just check as you go up one level each time, you are just getting the same, you're capturing the same sets all the time.